So I'd like to work through a few examples in Chapter 7. Let's go ahead and get started with example 7.1. Determine the shapes of A, sulfur trioxide, and B, this iodine tetrachloride anion. So for the first one, and you'll want to draw the Lewis structure. And we've already practiced drawing Lewis structures, and just make sure that you're able to generate this structure here that I'm highlighting. Ultimately, what you'll get is some version of sulfur in the center, and an oxygen, a second oxygen, and a third oxygen, one of which will have a double bond, the other two will have single bonds, and then you will put lone pairs around the oxygens to make sure that they have an octet of electrons. Now, if you put the double bond on the left, the up and down, or the right, it doesn't matter. It's the same representation. So you'll need to look at a chart, and this chart is clearly laid out in the activities and labs that we've went through. So just look back over that. And what you'll find is you have 3 attachments to this sulfur group, 1 double bond, and 2 single bonds. And then you will find which category that fits in. For the second structure, and we'll solve that in a second. The second structure, the Lewis structure, will have iodine in the center, and then we'll have a chlorine on the top, bottom, left, and right. Each of the chlorine will have sets of electrons around to make sure they have the octet. You'll notice that when you add up the total number of electrons, you have extra, so then you'll put those on the central atom. When you draw the Lewis structure for an ion, be it positive or negative, as a general rule, you'll want to put brackets around it, and then put the charge on the outside, as denoted here. You'll also notice in this example, it has 6 total things attached to it. We have 4 chlorines and then the 2 lone pairs. This would be 4 single bonds and 2 lone pairs. So then you'd find which category that fit in. So take a moment, look those up, and make sure they agree with what we show you on the next slide. All right, so for part A, according to, and it's a VSEPR model, and that stands for valence shell electron pair repulsion, VSEPR. With 3 electron domains, you'll arrange those in trigonal planar type geometry. Since there are no lone pairs on the central atom in sulfur trioxide, the molecular geometry will be the same as the electron geometry. Therefore, the overall shape will be trigonal planar. For part B, we'll have 6 electron domains. That fits into the category of the octahedral type geometry. However, since we do have lone pairs, the molecular geometry will be different. So our electron domain geometry is octahedral with 6 attachments. And then the molecular geometry that fits for 4 atoms attached and 2 lone pairs will be square planar, as shown here. And again, just make sure you're familiar with all of those in the tables, and you can refer to them. I don't require you to memorize them. Second example, acetic acid, the substance that gives vinegar its characteristic smell and sour taste, is sometimes used in combination with corticosteroids in treatment of certain types of ear infections. The Lewis structure has already been generated for us, as shown here. We have a carbon with 4 attachments, 3 hydrogens, and then another carbon. This carbon has a carbon on the left, an oxygen on the right, an oxygen above that has a double bond, and then there's a hydrogen off on the end. What you need to do is to determine the molecular geometry about each of the central atoms, and then determine the approximate value of each of the bond angles in the molecule, and then which, if any, of the bond angles would you expect to be smaller than ideal values. Strategy here, looking at the leftmost carbon atom, which is here, that'll be surrounded by 4 electron domains, 1 carbon-carbon single bond, and 3 carbon-hydrogen single bonds. The middle carbon, is shown here, will be surrounded by 3 electron domains, 1 carbon-carbon single bond, 1 carbon-oxygen single bond, and 1 carbon-oxygen double bond. And then our oxygen atom, shown here, is surrounded by 4 electron domains, 1 oxygen-carbon single bond, 1 oxygen-hydrogen single bond, and 2 lone pairs. So again, take a moment, find what the geometry would be around each, and then also look at the bond angles. So our solution. The electron domain geometry of our leftmost carbon, which is this one, will be tetrahedral with the 4 attachments. Because all 4 electron domains are bonds, the molecular geometry of this is the same, which is tetrahedral. The electron geometry of the middle carbon, which is this one, will be trigonal planar. And again, because you have domains that are all bonds, the electron domain geometry and molecular geometry will be the same, which is trigonal planar. And the electron domain geometry of the oxygen atom, which is shown here, will be tetrahedral with 4 groups. However, since we have 2 bonds and 2 lone pairs, the molecular geometry will be bent. The bond angles will be determined using the electron domain geometry. Therefore, the bond angles for the leftmost carbon, which is here, for tetrahedral should be 109.5 degrees. The middle carbon goes on trigonal planar, and that should be 120 degrees. And then with the oxygen, you'll see 109.5 degrees. The angle between the 2 single bonds on the middle carbon will be a little bit less than 120 because the double bond repels the single bonds more strongly than they repel each other. And also the bond angle between the 2 bonds on the oxygen will be a little bit less than 109.5, and that's due to the fact that the lone pairs on the oxygen repel the single bonds more strongly than they repel each other, therefore pushing the total bonding pairs closer together. And all of the angles are labeled here. Alright, so example 7.3, determine whether phosphorus pentachloride is polar. Now, to be able to do this, you'll want to first draw the Lewis structure. And then you'll want to find and look at each of the bonds and determine the more electronegative element in each bond. And then you'll draw a vector towards the more electronegative element in each bond. And then you'll examine the dipoles. Alright, so again, strategy, and I'll read through this, and it just summarizes what I just mentioned. To first draw the Lewis structure, you'll use the Vesper model to determine the molecular geometry, determine whether the individual bond dipoles cancel. So for part A, the Lewis structure of phosphorus pentachloride will have phosphorus in the center. You'll have all 5 chlorines attached. This does exceed the normal octet, and we've seen that before with phosphorus. Each of the chlorines will have electrons, which they all have their octets once you put the electrons around them. And what they've already done in this picture is they've shown these arrows, which should be vectors. Usually you'll just draw a little line, perpendicular line right at the end of the arrow that specifies that the arrow goes in one direction. It'll be pointing towards the chlorine because we know chlorine to be more electronegative than the phosphorus. So with 5 identical electron domains around the central atom, the electron domain and molecular geometries are both trigonal bipyramidal. The equatorial bond dipoles cancel each other, which are these 3 here. So you have one going this way, one going down to the left, and one going down to the right. And if you spin this around like a top, right where I'm showing here, and you stop it, you won't be able to distinguish these 3 chlorines that I'm highlighting from each other. So those 3 dipoles will be identical, and they pull in each of their own directions. And if you make a model or look up a 3-dimensional model online to convince yourself, you can see that. And the equatorial bond dipoles, which is this one that's above and below, will also cancel out. from one another, equatorial and axial. Equatorial, I believe I labeled the wrong ones, are the horizontal, which are these three, and the axial, which is like a spinning on an axis, is the up and the down. So since all of the dipoles cancel with one another, the PCl5 is therefore nonpolar. We have a second example, and it's to determine whether H2CO, which is a carbon double bonded to an oxygen in the structures below, and it is a type of aldehyde. This is called formaldehyde. Now, knowing the name being formaldehyde, you wouldn't learn that until organic chemistry, so don't worry about the naming here. So, to determine if this is polar, the first thing you do is draw the Lewis structure, and then, just like before, use the Vesper model to determine the molecular geometry, and then draw in your dipoles based on electronegativity. Our Lewis structure is shown here. It has carbon, hydrogen, hydrogen, double bond oxygen. Dipoles will go from hydrogen to carbon because carbon's more electronegative than hydrogen. So there's two of those. And then you have the oxygen going up. If you notice, since we have the hydrogen going towards the carbon, it's going inward and upward. So overall, you have an upward pull, rather than if they were pulling in the opposite direction, they may somewhat cancel one another. So the bond dipoles, although it is symmetrically distributed around the carbon, are not identical, and therefore will not sum to zero, and this will ultimately be polar. One thing to remember is to make sure that your Lewis structures are correct, and that you count electron domains in the central atom carefully. This will give you the correct electron domain and molecular geometries. Molecular polarity depends on both the individual bond dipoles and the molecular geometries. So draw your Lewis structure. Make sure you understand the bond angles in it, because that does play a role in when the dipoles cancel. And make sure you point the arrow towards the more electronegative element. All right, let's take a look at the next one, 7.4. What kind or kinds of intermolecular forces exist in these four compounds? Strategy here is to draw the Lewis dot structures and then apply Vesper theory to determine whether each molecule is polar or nonpolar. One thing to remember, and you'll see this in this chapter, is nonpolar molecules exhibit what's called dispersion forces. And dispersion forces are also called London dispersion forces, and they exist in every molecule. However, when it's a nonpolar, that's the only force they have, and it's a very weak force, but that's it. However, polar molecules have more than dispersion forces. They also have dipole-dipole attractions because of their polar differences. And if they have a hydrogen directly attached to a nitrogen, oxygen, fluorine, and sometimes sulfur, they will also have something that's called hydrogen bonding. So let's just jump right in and look at the Lewis structures of each of these, and then we'll look at each one and determine what intermolecular forces are present. So here's our structure of this first compound. This is carbon tetrachloride. It has a carbon in the center, 4 chlorines. Here we have this is acetic acid. It's vinegar. It has a carbon double bond O, carbon here, and then an OH. We can look at the geometries at these 3 positions, which we already did a couple moments ago. Here is acetone, and we have 3 central atoms that we could examine. And this is hydrogen sulfide. Looks just like water, except instead of an oxygen, you have a sulfur. So if we look at A, carbon tetrachloride, it's nonpolar. If we drew in the dipoles, and they're not drawn, but they would go towards the chlorines and they would all cancel out from one another. Since it all cancels out, it's nonpolar overall, and since you say it's nonpolar, then the only intermolecular force that's possible is dispersion forces. So one thing to get in your head, nonpolar, dispersion forces only. Part B, which is acetic acid, we have part of it is nonpolar and part of it is polar. If you look at these three situations here, this part of the molecule is nonpolar, but then with these oxygens, we'd have a dipole going towards this oxygen and towards this oxygen. So it would be polar. So one, it's polar, so we know that we'll have dipole-dipole forces. And then the other thing to look for is a hydrogen directly attached to either an oxygen, a nitrogen, or a fluorine. And then also you'll see it with sulfur as well in some cases. So since we do have a hydrogen directly attached to an oxygen, I'm highlighting it right here. This will have not only dispersion forces, because those are present in all molecules, it'll have dipole-dipole and hydrogen bonding. So 3 intermolecular force types. Part C, which is acetone, this is polar, and the major dipole is going to be the carbon going towards the oxygen, carbon double bond O. It does not contain a hydrogen directly attached to a nitrogen, an oxygen, or a fluorine. So there's no hydrogen bonding, but because it's polar, it'll still have dipole-dipole interactions. So our 2 intermolecular forces here are dipole-dipole and dispersion. And then our last case, this is polar. It's bent. It's just like water. Water's polar. This is also polar. And it does not contain a nitrogen, oxygen, or fluorine directly bound to a hydrogen. So it doesn't have hydrogen bonding. However, I did mention that sulfur is another one. It's just not mentioned here. So it's weaker hydrogen bonding than the rest, but it's still possible. But we'll just go with this slide and not be too technical. And we'll go with nitrogen, oxygen, and fluorine. A good way to remember that is NOF, N-O-F. Not a hydrogen directly attached, so no hydrogen bonding. And it would just have dipole-dipole and dispersion. So to go through again, nonpolar is dispersion only, which is this first one. This second one has dispersion, dipole-dipole, and hydrogen bonding. Third one has dispersion and dipole-dipole. And the last one has dispersion and dipole-dipole. Moving on to the next example, hydrogen selenide, which is H2SE, which is selenium, is a foul-smelling gas. It can cause eye and respiratory tract inflammation. The hydrogen-selenium hydrogen bond angle is approximately 92 degrees. Use valence bond theory to describe the bonding in this molecule. Strategy here would be to look at the ground state electron configuration. So this is going back to drawing out your SPD orbitals and using the electron configuration abbreviations. You can also look at orbital diagrams, both of which are shown here. Here's the electron configuration. It's abbreviated version. It's starting at argon, so it has argon with brackets, 4s2, 3d10, 4p4. If we look at just the valence electrons of it, and not even just the valence, but just the p of the valence, which is 4p4, the orbital diagram is here. Now we know the p orbital has 3 types. You have your px, your py, and your pz. And then when you fill this according to Hund's rule, you'd fill 1, 2, 3 electrons, and then here would be the 4th electron. So from the orbital diagram, we can get a little bit of information here. And the solution would be 2 of our 4p orbitals are singly occupied, and I'm highlighting those here, and therefore available for bonding. Available for bonding because they have an empty spot open. Therefore, the bonds in our hydrogen selenide form as the result of the overlap of a hydrogen, 1s orbital, with each of these orbitals on the selenium atom. And then one thing to remember is because the 4p orbitals on the selenium atom are all mutually perpendicular, we should expect the angles between the bonds formed by their overlap to be approximately 90 degrees. So just an application of that. I have a table that I just wanted to go through, and I wanted to mention a couple things that you can do, and this is looking at hybridization. There's a pretty easy way for hybridization to or to determine hybridization just based on how many things are attached. So if we have, and look at this with me, number of electron domains in our central atom. And so just how many things are attached. Also include lone pairs. So this would be how many electron domains do you have? If you have 2, then it's sp. If you have 3, it's sp2. 4, sp3. 5, sp3d. And 6, sp3d2. One thing that I want to show you, and let me get my drawing tool. It's pretty easy if you write out each of these letters, and this drawing tool doesn't let me draw it very nicely, but I think you can see this has 2 letters, S and P, 2 electron domains. With the sp2, that would be like S, P, and P, and that's 3 letters. So 3 letters, 3 electron domains. You can probably see where I'm going with this. For 4, we should have 4 letters, which would be S, P, P, P. 4 letters, 4 groups attached. And then this would be 5 letters and 6 letters. We'll just draw these out. This would be S, P, 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 D. And then the last one, S, P, 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 D, D. So then that would be 6 letters. All right, so our next one, and I got moved around here, 7.6. Ammonia, which has the chemical formula of NH3, is a trigonal pyramidal molecule with a hydrogen-nitrogen-hydrogen bond. The angles are going to be about 107 degrees. Describe the formation of 3 equivalent nitrogen-hydrogen bonds and explain the angle between them. And we'll also do hybridization, since I just mentioned that as well. Strategy here, starting with the Lewis structure, determine the number and type of hybrid orbitals necessary to rationalize the bonding in NH3. So here's our Lewis structure that you should be able to generate. And you'll have nitrogen, hydrogen, 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 only 1 bond to hydrogen. And then you'll have 2 electrons left to put onto the nitrogen. Hydrogen has a duet of electrons. And the nitrogen has an octet of electrons. If we look at our electron configuration, and going from the nearest noble gas, it has helium in brackets, 2s2, 2p, 3. The orbital diagram just of the valence electrons would look like this. We have 2s2, 2p3. So these would be available for bonding, but this would have 3 bonds, 1, 2, 3, but it doesn't take into account the lone pair. So this gets into where we need to actually mix these together to ultimately produce our hybrid orbitals. Now I'm going to go through a pretty detailed description, and just read along with me on these next slides, and then I'll just simplify it very easily for you using that counting method I showed you with the table. So although the nitrogen atom has 3 unpaired electrons needed to form the 3 nitrogen-hydrogen bonds, we'd expect bond angles of 90 degrees and not 107 to form from the overlap of the 3 perpendicular 2p orbitals. However, with hybridization, it will change the scenario, and that's necessary to explain our bonding. Although we often need to promote an electron to maximize the number of unpaired electrons, no promotion is necessary for the nitrogen in ammonia. We already have the 3 unpaired electrons necessary, and the promotion of an electron from the 2s orbital to one of the 2p orbitals would not result in any additional unpaired electrons. Furthermore, there are no empty d orbitals in our second shell. According to the Lewis structure, there are 4 electron domains, as you saw with the 3 hydrogens in the lone pair on our central atom. 4 electron domains on the central atom require 4 hybrid orbitals, and 4 hybrid orbitals require the hybridization of 4 atomic orbitals. One thing to remember is, however number of atomic orbitals you'd use will be the number of hybrid orbitals that you produce. This will ultimately correspond to an sp3 hybridization because the atomic orbitals involved in the hybridization contain a total of 5 electrons. We place 5 electrons in the resulting hybrid orbitals. This means that one of the hybrid orbitals will contain a lone pair of electrons. All right, so what they've shown here is they've taken 1, 2, 3, 4 atomic orbitals, and they've produced 1, 2, 3, 4 hybrid orbitals. So we take 4, we get 4. If we take 2, we get 2. If we take 3, we get 3, and so forth. This needed a total of 4 because we have 4 groups. Now, I just went through a pretty big, long explanation. However, if we get our drawing tool, and let me draw ammonia. So if you go from the Lewis structure, and let's see, let's put a box around it. Here's our central atom. We have 1, 2, 3, 4 attachments. The only one of those hybridizations that has 4 is an S, a P, a P, and a P. Which would be, you have S, 1, 2, 3, 4, and that comes out to be S, P, 3 hybridization. So a very easy way to do it is to draw your Lewis structure and then count how many things you have attached so that you can get your hybridization. I'm going to go back and just show you one more time. Here we go. So we have 2, 3, 4, 5, and 6 electron groups. So we had 4 on ammonia. You had the lone pair and the 3 hydrogens. So then that would be sp3. So just look at the groups and then that would be how many you need. You always have one S and a P, and you don't have any more than in just one of the S. You'll notice it's S, 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 and S. The P will increase until you get to 3. So you start with SP, SP2, SP3. Once you hit the third one, then you add D, and you'll only go up to D2. So just to go through this long explanation and then show you a little picture or graphic that's represented. Each nitrogen-hydrogen bond is formed by overlap between an sp3 hybrid orbital on the nitrogen atom and the 1s atomic orbital on a hydrogen atom. Because there are 4 electron domains on the central atom, we expect them to be arranged in a tetrahedral-like geometry, which is ultimately 109.5 degrees. And then because of the lone pair, it's going to distort that angle slightly. Instead of 109.5, it comes out to be 107. Now, to take the table that I showed you, where you figure out the electron domains, you will look at the valence electrons and look at the orbitals that are used in the highest energy. And then if for sp3, you're going to use a total of 4 boxes. And then you redraw those and call each one sp3. If you had sp, you would use 1s and 1p and combine those together, and you would get 2 boxes and call those sp. And you can draw those out for each of them from that table to really wrap your mind around it. Let's look at the next example. Thalidomide, which has the chemical formula C13H10N2O4, is a sedative and antiemetic that was widely prescribed during the 1950s in Europe, not in the United States, and it was for morning sickness for pregnant women. Its use was largely discontinued due to some really terrible birth defects, and it would cause babies to be born without arms and legs. Really terrible. You can look up some more information if you're interested. But we're using this structure to determine the number of carbon-carbon sigma bonds and then the total number of pi bonds in thalidomide. You may want to look up some information, just some background info on sigma and pi. We're going to touch the surface of it. You get into more detail in organic chemistry with this, but a sigma bond is a single bond. It's easy to remember because sigma and single sound similar. And then a pi bond is a double bond. And then a triple bond will contain 2 pi bonds and 1 sigma bond. And a double bond will contain 1 sigma bond and 1 pi bond. A single bond, only 1 sigma bond. So again, I just mentioned that, but strategy, remember a single bond is composed of a sigma bond, whereas a double bond is usually composed of 1 sigma and 1 pi. So our solution here, thalidomide, contains 12 carbon-carbon sigma bonds and a total of 7 pi bonds. One thing that they didn't mention, but I guess just assume that you know, is they're using what's called this line angle drawing. And what a line angle does, and this is something that you would learn in organic chemistry if you take it, it's an abbreviated form of drawing these out. It's a shorthand, if you will. And what it does is every one of the points represents a carbon, and then the hydrogens are just assumed to be there. And then it takes into account that carbon usually forms 4 bonds. So for example, on this point that I'm highlighting, we have a double bond and a single bond. So that's a total of 1, 2, 3. So that would mean that there's one more imaginary bond, or it's not really imaginary, but invisible, that you can't see in the drawing. And there'd be a hydrogen there, but just not in the structure. If you look around at everything that is not labeled other than oxygen and nitrogen, you find the carbon. And so we can find these single bonds and double bonds. So we have 1, 2, 3, 4. Let's see, 5, 6, 7, 8. And how many did they say? 12. So I guess they're including these as well. 9, 10, 11, 12. So it's not really carbon-carbon sigma bonds. It's 8 carbon-carbon sigma bonds, and then you got, what, 1, 2, 3, maybe 9. Maybe 9, and then 3 more. Where you have a carbon-nitrogen bond, but you get the point. And then you have 7 pi bonds, so that would be where our double bonds are. 1, 2, 3. Then we have 4, 5, 6, 7. So pretty easy to do. Just count out where the single bonds are and where the double bonds are. One thing that you can do is to think about it is the Lewis structure given for thalidomide is one of 2 possible resonance structures. You can move those double bonds around in the structure to draw the other resonance structure. And your sigma and pi bonds should be the same. So you can do that if you want to. Let's take a look at the next example, 7.8. In addition to its use in aqueous solution as a preservative for laboratory specimens, formaldehyde gas is used as an antibacterial fumigant. Use hybridization to explain the bonding in formaldehyde. And we looked at this structure earlier, CH2O. Here's our Lewis structure again, has carbon, hydrogen on the left and right, and a double bond oxygen up top. The carbon and oxygen atoms have 3 electron domains around them, and we can see here's carbon 1, 2, 3. The oxygen would have lone pair, carbon for those 3. So we have 3 electron domains. So since we have 3 things, that would be, the hybridization would need to be sp2. So look back at that table, and you would see that it would need spp, which is 3 letters. For the carbon promotion of an electron from the 2s orbital to the empty 2p orbital is necessary to maximize the number of unpaired electrons. For oxygen, no promotion is necessary. Each undergoes hybridization to produce sp2 hybrid orbitals, and each is left with a single occupied unhybridized p orbital. Now, that was a mouthful. Let's look at this just visually. I think a visual explanation would be helpful. Here's carbon and here's oxygen. This is just looking at their second energy level s and p type orbitals. And carbon should have 4 valence electrons, and oxygen has 6. So we can see we have 1, 2, 3, 4. Now, we're going to be forming sp2 hybrid orbitals, and you're going to use 3 blocks to form 3 blocks. So if you look at the dotted part, we're not going to use all of it. We're just going to use an S, a P, and a P to match this sp2. And then we get our, as I highlighted in green, our sp2 hybrid orbitals. But we still have this unhybridized orbital left over. So this is a little bit different than the last one that we looked at that had sp3. You took 4, you made 4, and the result gave you all hybrid orbitals. You don't have to hybridize everything. You only hybridize what you need based on how many groups there are. So we had 3 groups, you use 3 boxes, and then you have this left over. When we redraw this, as shown here, we have a total of our 4 electrons. You put those in 1, 2, 3, and then you have this other one. It is slightly different energy. When you get to organic chemistry, it may do this a little bit differently, but I'll save that for later. And you get this representation. So for oxygen, we can do the same thing. We use 3 boxes. So here's our 3 hybrid. We're left over with this one, so that's shown here. And then we take our electrons, 1, 2, 3, 4, 5, 6, and we got 1, 2, 3, 4, 5, 6. So one thing I will say is the electrons that have been inside the part that's dotted are the ones that you hybridized. Those are the ones that end up in our hybrid orbitals. This one that's outside stays outside. This one that's outside stays outside. Within the hybrid area, you got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So looking back at the explanation, you can kind of see what it's mentioning with the single occupied and unhybridized p orbitals. What we have with this is a sigma bond will be formed between the carbon and oxygen atoms by the overlap of one of the sp2 hybrid orbitals, and I'll show you a picture below, which don't get overwhelmed by the picture. This is more organic chemistry down at the bottom. 2 more sigma bonds form between the carbon atom and the hydrogen atoms by the overlap of carbon's remaining sp2 hybrid orbitals, with the 1s orbital on each hydrogen atom. Finally, the remaining p orbitals on carbon and oxygen overlap to form a pi bond. So here we have our carbon to oxygen sigma bond, which is this one. These are all the green. These are the lone pairs on the oxygen, sigma bond to hydrogen, and then this blue part represents our pi bond. A pi bond actually is split up into 2 separate interactions, an interaction above and below. Again, this is more organic chemistry. For your part, if you can find the table of the 2, 3, 4, 5, and 6 attachments and state whether it's SP, SP2, SP3, SP3D, or SP3D2, then you're in perfect shape. One thing just to take home about this is our analysis describes the formation of both a sigma bond and a pi bond between the carbon and oxygen atoms. Corresponds correctly to the double bond predicted by our Lewis structure. Alright, so let's look at the next example, 7.9, and we got just a little bit left. It's a pretty long video. Hopefully you've been watching this in intervals. The superoxide ion, O2-, has been implicated in a number of degenerative conditions, including aging and Alzheimer's disease. Using molecular orbital theory, determine whether the superoxide ion is paramagnetic or diamagnetic, and then calculate its bond order. So the strategy here is to start with the molecular orbital diagram for oxygen, and then add an additional electron because it is charged with this minus. For now, I'm just going to have you look up the molecular orbital diagram until we look into more detail on how to generate these. So here's the molecular orbital diagram for oxygen, and we have, you may have to zoom in on it, but it goes from lowest to highest. It's very similar to an orbital diagram, the atomic orbitals, using the 1s, the 2s, and so forth. They have different names, which are listed here on the right side. It's different naming convention for these molecular orbitals. But without getting into any more detail, I'll show you something, and directly from the slides does talk about bond order and such. So anyways, in this case, either the two singly occupied pi star 2p orbitals can accommodate an additional electron, which is listed here. There's an open spot there. This gives a molecular orbital diagram in which there is one unpaired electron, making our superoxide ion paramagnetic, kind of going back to diamagnetic versus paramagnetic trends. The new diagram has 6 electrons in the bonding molecular orbitals and 3 in antibonding. So one thing to mention with this, the ones without the stars are bonding, and the ones with the stars are antibonding. And then you can subtract from one another and divide by 2 to get bond order. We'll ignore the electrons in the sigma 2s and the sigma star 2s orbitals because their contributions to the bond order cancel each other, which are these two here. Okay. So what we have left over, you'll have 6 minus 3 divided by 2 equals 1.5. So our bond order is 1.5. Bond order means how many bonds exist between them. So if it's a bond order of 1, it's a single bond. Bond order of 2 is a double bond. Bond order of 3 is a triple bond. If you have like a half bond order, it's somewhat in between the like single and double bond. So experiments confirm that the superoxide ion is paramagnetic. Also, anytime we add 1 or more electrons to an antibonding molecular orbital, as we did in this situation, we should expect the bond order to decrease. Electrons in antibonding orbitals cause a bond to be less stable. All right, one more, and we'll try to wrap this up in hopefully around 45 minutes total. 7.10, it takes 3 resonance structures to represent the carbonate ion, which is CO3 with a -2 charge. Here's our 3 Lewis structures, and the only difference is just the movement of the electrons in this double bond. So we have 1, 2, and the 3rd resonance structure. None of the 3, though, is a completely accurate description. As with benzene, C6H6, the bonds that are shown in the Lewis structure as 1 double and 2 single are actually 3 equivalent bonds. Use a combination of valence bond theory and molecular orbital theory to explain the bonding in the carbonate ion. So again, the strategy, first thing you want to do is take the Lewis structures and determine how they must be sp2 hybridized. So looking at those structures again, and maybe draw them out and come back to this slide if you want. Each will be an sp2 hybrid orbital on the carbon atom, which overlaps with a singly occupied p orbital on an oxygen atom, forming 3 sigma bonds. Each oxygen atom has an additional singly occupied p orbital perpendicular to the one involved in the sigma bonding. The unhybridized p orbital on carbon overlaps with the p orbitals on oxygen to form pi bonds, which have electron densities above and below the plane of the molecule. Because the structures can be represented by resonance, we know that the pi bonds are delocalized. So really with this, and they've looked at it really in detail, you can just determine what the hybridization is based on the electron groups attached. You got 3 groups, and it should be sp2. So although the Lewis structure of carbonate shows 3 electron domains on one of the oxygen atoms, we generally do not treat terminal atoms as though they are hybridized because it is unnecessary to do so. Just sp2 hybridization. That wraps up chapter 7 again, some of this did go into the realm of organic chemistry, and don't be too overwhelmed with it. And we will practice more activities and look at things with our experiments. And some of the information here, you don't need to go. Don't fret about it too much. Really, if you first thing to focus on is that table with your hybridizations, and if you're doing that, then you're in pretty good shape. One other thing to mention is that the third exam will be a take-home exam, and so some of the information, while it may be overwhelming, you'll be able to have lots of resources to be able to look up some aid as you work through your solutions. I hope this video was helpful, and I will see you all at our next meeting. Thank you.